And I've been observing this for a while, and the speed over ground is constantly around 1 knot less. So it goes up and down because we're surfing down the waves. But anyway, you'll find that speed over ground keeps being smaller. So the reason is we're having the current against us, which is, very interesting, because we all know that, the winds are blowing like this, and then in Atlantic you should have this, North Atlantic current going here. So everything makes sense that the current should go like this, but we're actually having current up against us. So I guess, these currents kind of, make some eddies here, turn for some reason. So now we're trying to get the latest weather forecast via Iridium. So we have selected the area, because we don't want to download all the weather in the world. So we've selected the area and which model. And now the signal just came back, so we have full signal because we've just lost it earlier. So now we're downloading the latest weather forecast. And this is our, so Iridium, this is our satellite modem, or how I call it. But it takes time. So now this is loading. The red bar has to come to the end, and then the next 3. So we're getting there. Oh yeah, we just lost the signal, it's red. So here it is, the latest forecast. So we are here and we go here. So these are the routes that are like options you can take. And here you can choose the different models, because it's all mathematics, so there's different models. And each model tells you a little bit, different. Whoop. That's a little bit zoomed out. So yeah, what we're getting it looks like, so now we're gonna go forward in time. And then you can see how the wind is gonna change. So yeah, the direction stays the same. It's gonna drop a little bit. So we're back in the game. We just put up the spinnaker, and now the boat starts flying. You can see no engines, only using a spinnaker. So we're flying Gennaker only now, and we have a pretty good apparent wind angle. You can see it's kind of from the side, a little bit from the back. Well, the wind just dropped to 14. We're doing 8 knots, speed over ground. And as the wind increases, we go more. So now we're on 15 through wind speed. We're doing over 8 knots. That's pretty good, and that's just with Gennaker. We don't have mainsail up, and it's pretty cool. Vacuum cleaning. Always nice to have a clean boat. So the fruit is doing, okay. Every day 2 oranges have to go away, and a couple lemons because they get really bad. Now the carrots are slowly, now after 5 days, getting some of them pretty soft. We'll have to finish them. Bananas are they look bad, but they're still okay. Apples are doing really well. And tomatoes started quite badly, but down there just keeping up, so it's okay. And these cucumbers, they seem to be a little bit softer. That's fine. Perfect view. And luckily we have the shade because the sun, we're going more south. So we keep this side of the boat in the shade. And feels great. Feels comfortable, safe. I just love the setting layout of this, cockpit area. Another beautiful day. I've done a super cool thing yesterday, so I determined our position just by using a watch and this list of paper, and that's include longitude and latitude. And actually it works, and it's pretty simple. So what I did is using this watch, which is set to GMT, which is the Greenwich time, the 0 meridian, and then I timed the moment when the sun came up, so the sunrise. And then I timed the sunset. Now, if you go in between and get the time in the middle, this is when the local noon was at my meridian. And because I know that at Greenwich meridian, the local noon was actually 16 minutes to 12. It's not always at 12 because there's some equitation of time. It can vary, you know, like 5 minutes more or less. Anyway, just by doing that, I can calculate our longitude, so the distance from the Greenwich. And I actually have a pretty cool table which helps me, but you don't need any table. So this is just, you know, conversation of arc to time, which basically says that, you know, 1 degree of longitude is equal to 4 minutes in time of sun. So which makes, let's say, in 1 hour, the sun travels 15 degrees of longitude. So it actually worked. I mean, I had a problem that when I was timing the sunset, there were clouds, so I kind of messed it up for a couple of minutes. But in the end, the longitude was pretty accurate, you know, inside 60 nautical miles, which is not accurate. But I had the wrong reading, and I was doing it for the first time. But it works, so I'll do again today and see what brings. You know, I just want to improve my accuracy. And then also it's hard to see when it's exactly sunset, sunrise, just by, you know, watching by eye. And now we see that in 1 minute of time, we can get a 50 nautical miles error, right? So if I had 60 nautical miles error, that's just 4 minutes of wrong timing, and because there were clouds, I couldn't do it. But anyway, it works, and I'm gonna be more accurate today. And then how I got latitude from this, which is a little bit more tricky without the sextant, but it's actually pretty simple. So because I knew the time of sunrise and the time of sunset, I know the length of the day. And then in Almanac, which, you know, it's for every day, this is for 3 days from 9 to 11 November. So you get sunrise and sunset for every latitude. So this is to help you to catch, you know, nautical twilight, civil twilight when you're, you know, using sextant for the stars. But anyway, so we all know that right now, because the sun is south, declination is 17 degrees, we all know that the more north you go, like you go to Norway, the day is shorter and shorter, and the more south you go, the day is longer and longer, right? So just by knowing the length of the day, which you calculate from here, you can determine your latitude. And I did that, and I was actually pretty accurate. I mean, this table is not accurate because it goes in 10 degrees. You see, like 10, 20, 30 degrees north. So my calculation was, I'm just a little bit about 20 degrees, and that's where actually we were. We were around 21. So if I had a better table, or if I interpolated these numbers, I would be super accurate. So I have a good feeling that actually just by watch, now this is all emergency navigation, but you see, just with the watch, you can get super easy longitude, but has to be set on Greenwich. You still need to know the Greenwich time. And then if you have these tables, which you just might have on a boat, you can very easily get your longitude. So we just got our coordinates with a piece of paper and the watch. No sextant, no tables, and it works. I just have to improve my accuracy. Another great thing on this boat is this area, and you can use it really well while sailing. So we're now flying the Spinnaker, and I really want to be close to the helm in case something goes wrong, you know. So I don't want to sleep in the Emma. And so I just lay down here, and I have this beautiful terrace, and I put this over my eyes to keep it more dark, and it really works very well. Super comfortable here. It's wide enough, long enough, silent, and it's not moving much. Really good spot. And you can also, you know, just sit like, it feels just like being at home, you know. It's so comfortable, this area. And it's actually a good spot because you can still see the sea horizon. It's a, you know, beautiful view here. And you can just relax and be super close to the helm. You get a lot of fresh air through the doors. And then just, you know, take a nap, put the curtains off, lay down, and take a short nap. So I kind of like healthy food, but I don't usually take much time to prepare. So no, I just take whatever's healthy. I just wash it, peel it and eat it. And that's what I would do. So that's a great way to have a healthy meal. Just eat raw food, and it's simple. I mean, it's usually better if somebody prepares it for you, cuts in small pieces. But it's great stuff. You get healthy stuff, and you get good carbs. And then just add some protein, and you're good. Healthy diet. You're not burning much calories when you're on the sea. Sailing is usually gaining weight, and then back home it's losing weight, walking up to the mountains. Well, as I've said, we've started one day later because we didn't want to be hitting 45 knots the first day, but most of the boats left. I think maybe 2 boats stayed in Gran Canaria, but let's say around 90 boats left, and now we're slowly catching up to the fleet. The first boat actually finished already. We have 2 boats here on AIS. One is Doubleton. So it's a 30-meter sailboat. They're doing 4 knots right now, and we are doing 6. And you can actually see them down there. They're flying a very big spinnaker. Doing really well. But we're slowly catching them. We have around 1.5 knots more speed using this Gennaker alone. And then there's another boat, Stella, which we already saw earlier. So let's see what's Stella up to. Stella is doing 4.6 knots right now, and it's an 11-meter sailboat. So actually doing really well. It's not that big boat. I mean, it's still decent size, but one of the smaller boats on this Rayleigh. And we've lost visual, and they were not flying any spinnaker. They just had a normal sail, so that's why they're a little bit slower. This boat has quite a lot of extras. So this is for safety. We have Ep.3. That's not an extra, that's a necessity. So when you trigger this, it's going to send a signal via the GPS that we're in trouble and we're asking for help. And then this is kind of cool stuff. This looks like an old Soviet, whatever, high-tech machine. It's basically just a time watch. So you set, let's say, 20 minutes, counts down, and then goes really loud. So if you're sailing solo and you want to have just a 20-minute nap, this is definitely going to wake you up. And then here we've got a couple of really cool stuff. So this is again, looks like an old Soviet VHF. And we have another a little bit more modern here. But I say, this old quality, this is ICOM. There's lots of dust. It's a really old one. They go far. They work forever. Whatever was built in the old days works forever. And we have a couple of lamps. You never know when you use them. And there's another light, more like spotlight. And we have this really cool, it's a Steiner. It's one of the best binoculars you can have. Really quality. And then one of the coolest things in this shelf. This is a FLIR, it's a night watch. So this is actually a thermovision camera, so you can see at night. And really, really cool stuff. But also pretty expensive, but when you need it, you need it. And then it's worth every cent. And then we have this grab bag. And let's see what's inside. So there's this is a dry bag. And yeah, let's take a look what's in here. So we have sponges. I don't know why is this in here, but probably useful. So here we have medicine, travel kit, sunglasses. That's definitely useful. And then we have food. These are like loads of peanuts. And then we have this, flares and signaling. And then we have this horn, duct tape. And then we have more snacks, just in case, it takes a little bit longer in life raft, so there's something to do, you just snack while waiting. We have toilet paper, and there's only one, so It's gonna be a big fight for this. Then we have some kind of tuna spread. So maybe you can throw this to the sharks so they don't eat you, they just eat the tuna. That's probably what it's for. And then we have a compass and a rag. A rag is probably just, to keep the life raft clean, put water out. But yeah, rag is always useful for all kinds of stuff. And then we have a couple of small things. Yeah, we have those blankets. So thermal blankets. Oh, and this is the chemical stick. It's good to have. And there's a little bit of ropes and a knife. So this is our grab bag. And of course, we would take some water. We have some canisters, so in case going to the life raft, you would take this, put Ep.3 inside, and then take some water, which is not in this bag. And also, you would probably throw in a VHF. So it's a grab bag, and it's actually not ready. It's more or less ready, but there's a couple of things that you have to add when leaving, so I'm not sure that's how it should be, but I don't know. Now this is a really good example of what you actually see on the radar. So this is ice, so whenever you have this kind of ship shape and these small lines, this is from ice. And then on radar you can still see ice, so this is not radar. So what radar sees is actually only, you see this spot, like this is some strange reflections, not sure what it is. But you see this reflection, this is the boat. So that's how you see boat. Let's go bigger. Okay, so now the radar is set on 4 nautical miles, which means we can see 4 miles ahead. And now this is it. So this is the boat that we can see down there with the spinnaker, Doubleton. And if you forget about the shape of this boat, this blue mark behind, this is actually the reflection you're going to get from the radar. And you see the difference between this and this is actually pretty small. And this is actually false. This is either waves or because the gain is too much. And so you have to, use a common sense to use the radar. So now we are set on 12 nautical miles, and you can see immediately that because the range is so big, actually it's very hard to see. You see these small spots. The eye still works really well, but this is now ice system. So that's why you have to zoom in and set it to, let's say, 4 miles or 6 miles to be useful. And now you see this spot is much bigger because we're more zoomed in, and now things become useful. Slowly catching on this boat, and its name is Doubleton, and it's actually a catamaran. And as much as I can see from here, I might be wrong, but I think it's a Nautitech 46. And they have a parasail. My second attempt of getting longitude and latitude just using this piece of paper and the watch, timing sunrise and sunset, and then using day length in an almanac, gave me super accurate results. So my Finnish result tells me that that's my calculated longitude, and that is GPS, and this is only 5 miles error in longitude. It's wow, amazing. And I didn't time really well the sunset because there was clouds, so it was a little bit off, so pretty good. And then the latitude, so my length of the day where we are is 11 hours 15 minutes 40. And then because I don't have very accurate tables here, this is like every 10 degrees, so it's like rough estimation. Well, at 20 degrees you have 11 hours 13 minutes, so the difference is 2 minutes, which means we are just a little bit under 20 degrees north. And the GPS said 90 degrees 50, so this is pretty close, we're talking like inside 20 miles, maybe even less, like more or less very accurate. So let's go through what I did. So I had a sunrise, which was 7 hours 45:50. I had sunset, and then I calculated when noon was, because noon would always be in the middle of this. So the noon was at 1:13:40. And because I know that from a quotation of time that at Greenwich the noon was at 11:44, makes a difference 1 hour 29 minutes 40 seconds. And once you put this into the degrees of longitude, you get 22-25 west. So it's pretty easy. And then for the latitude, so the length of the day where we are is 11 hours 15 minutes 40 seconds. And then from Almanach, so I took at 20 degrees north, I have sunset and sunrise. And the length of the day theoretically at 20 degrees north is 11 hours 13 minutes, which is only 2 minutes 40 seconds less than what I have, which means I am under 20 degrees north, because now the day is longer if you go south because it's winter. So my latitude is something under 20 degrees north. I should do interpolation or just use more accurate tables. So that would be pretty easy. I just, didn't take time to do it. And GPS was, very close. So overall, pretty happy with the result. It's actually like super accurate. And this was my second attempt doing it. And yesterday I was inside 50 nautical miles or 60. Now I'm inside like 10-15 nautical miles, which is, I probably had a little bit of luck. We'll see in the next days. But it's just the proof that actually this method works. So you don't really need a sextant as long as you can time sunset and sunrise, so which means you shouldn't have any clouds. And all you need is a watch set on Greenwich, and you need to know what date it is. And then you need these tables for length of the day at different latitudes for different dates, and it's very easy then to find where you are. And you can get some avionic tables which have very accurate for every degree or even more. So pretty easy to, here I would have to interpolate, but there you just, find it very quickly. Day 6. Waiting for the sunrise, and for the last 2 days I was really lucky with the sunrise because I could time it, but sunset was always with the clouds. Let's hope in the third shot, that's today, I'm gonna make it with nice sunset and nice sunrise. So the winds have dropped during the night, we're just on the engine now, and we're getting really close to Cape Verde, to Mindelo. And the thing is actually that if we wanted to come during the day, we should start yesterday evening with 10 knots of speed. So we figured out we don't want to have a landing during the night. So we reduced our speed. We're just doing 5 knots. So we're just going to go super lazy, probably sail during the day if the winds go about 10 knots, and super slowly and lazy come tomorrow morning with the daylight, which is super recommended, especially when going to places you haven't been yet. There might be nets, there might be who knows what, so why would you just want to force it? We'll just, go slowly, come during the day. Another thing I'm practicing a little bit is actually, compass and, sunrise and sunset. So you would think that wherever the sun's gonna go up, that's east, right? Well, not exactly, because the sun has a declination. Declination means how far from equator it is. Everybody knows that 23.4 degrees when in summer the sun is north, right? And then in winter it goes south. So that's why in winter it's cold, right? Because the sun is south and then on the northern hemisphere. And then when the sun is north on 23.4, that's when it's the warmest in in Europe, in Mediterranean, northern hemisphere. So the thing is that actually where the sun goes down or up, it's not exactly east. It is only twice per year, and that would be at the equinoxes. That's when the day and night are just the same length. So these equinoxes, they show up on 21st March, you've heard about this, and 21st September. Heard about these dates, right? And then on 21st June, the sun is going to be all the way north, so it's going to be on 23.4 degrees, and that's the declination of the sun, which means that the sun is going to rise 23 degrees further up from east. So today I'm not lucky. You can see there's clouds already, so the sunrise already happened, and if it's only twice a day, you have to be lucky. See, the sun is there. And I have no clue, is it like Is it sunrise yet? It is not. Has it passed? And you have to be very accurate with these watches because every minute means a big error. So today, I'm afraid we're not getting any accurate results. Well, it's still beautiful sunrise, even though I couldn't time it. So the sunrise happened like using my compass on heading of 100 and let's say 15 degrees. So why like it doesn't make sense, right? As we said, it should be east, right? The sunrise is always east, which is 90 degrees, right? So how did you get 115? Okay, I was saying about declination. So declination right now is 17 degrees south. Okay, which means that the sun should theoretically rise 90 plus 17. And 90 plus 70 is 107. So there's still 8 degrees difference. We're still missing 8 degrees. And that is variation. So compass is influenced by deviation and variation. So deviation would be, let's say this is a steel rail. This is stainless, so not much effect. But if this is a steel, which is magnetic, and I put it close, of course it's going to affect the magnetic needle inside. So deviation is caused by magnetic objects around the compass. Variation is caused by just by Earth, you know. Like I know in the Mediterranean, variation is very small. Here, it's around 7 degrees. And oh, these are the 7 degrees we were talking. Now, as I'm using this compass and it's away from all the metal stuff, and so I can just assume deviation is 0. Okay, so I'm only worried now about the variation. I can read variation from charts, so very easy. But the question is, in a barefoot navigation, emergency navigation, you get lost, you have only this, and then you want to figure out what the variation is, and that's actually pretty easy. So to figure out the variation from sunrise or sunset, let's go for the sunrise. So the sunrise should be 90, right? But because the deviation, it's going towards winter, is 17 degrees south, then actually it should be 107 degrees. And then I measured, and I read 115. So it should be 107, and I read 7 to 8 degrees more. So this 7 to 8 degrees more is variation. And now I can use this variation for a couple of days because, you know, as we go towards Caribbean, I know it just goes up to 12, 13 because I know. So it's not like variation is now, it's just right now, right here, it's this much. So as you go, you know, a couple of days more to other direction, you can just, you know, check it or just check it every morning at the sunset. So now let's assume I had, you know, the boat sinks, emergency navigation. I'm in a small dinghy in the middle of nowhere. And it happens I have my watch because it was on my hand, and I have a compass because it was around my neck. So how can I, you know, help myself navigating? And let's say I have a small sail, so, you know, I can go a certain direction. Okay, so how can I navigate? I know approximately where I was, and approximately I knew my course, and, you know, I know like, okay, that's what, you know, where I was going. Or let's say I know that longitude of, I don't know, Caribbean is this much, and I know that latitude is something between 12 to 20 degrees north. So I'm just going to be using this thing. So using the watch, it's very easy. Of course, I need a pencil and a paper, but, you know, just using a watch, I can determine my longitude very easily by timing sunrise and sunset. So that's what I've done for 2 days now, and I find it pretty accurate. Now, just using a watch and the length of the day, I can pretty easily determine the latitude, but I need almanac, which is wet, so, you know, using that I cannot, you know, help myself a lot. But then there is a Polaris, you know, it's a star, North Star Polaris, which has more or less declination of 90 degrees, and let's, you know, forget fancy words. It just means like whatever the angle I take, if I find it on the 40 degrees angle, that means I'm on 40 degrees latitude, right? So if I can some kind of measure that with a stick or whatever, you know, I can know, was I going south or whatever my latitude was? Because before, you know, going into the laser, I probably knew my latitude, you know. Right now, I know we are around 19 degrees, 30 minutes north, so that's my starting point. And then by observing the height of the Polaris with some kind of stick during the night, I can tell pretty well if I'm going south or north, you know, the latitude. I'm going up or I'm going down. And then why is a compass good thing? You know, during the day you want to keep a certain direction. And now you can keep this direction like, I don't know, watching like, you know, nature, swell, wind, but everything is changing. And now as we figure out that I can actually figure out the variations, so use a compass pretty accurately, I can just, you know, keep the direction during the day, and then during the night check with the Polaris my latitude, and then you know, check my longitude using my watch and sunrise and sunset. So it sounds super, you know, kind of maybe complicated. Actually, it's very easy, and every day I feel more comfortable that you know, I would actually succeed in doing that. So we're doing around 5 knots. And this is 110 horsepower Yanmar, and we're running it on 1,500. And actually this is a cool engine because I can check the consumption. So right now, okay, so right now the fuel rate is 2.5, so we're using 2.5 liters per hour. So it's a 110 horsepower Yanmar engine doing 1,500 RPM, and that gives us a speed over ground of 5 knots. And this is Cape Verde, we are here. So we start from Canary Islands, now we're almost there. We go to Mindelo, and that's around 120 nautical miles to go, which is, let's say, 3/4 of the day. And this is how it looks. We're in the middle of ocean, and there's absolutely nothing, only the sea, clouds, sunrise, and a couple of fools on a trimaran trying to figure out if they can make it across an ocean and how is it going to be. So how to figure out latitude using, let's say, Polaris at night or whatever without anything. First, you have to calibrate your hand and whatever device you're going to be using. So that's really good to be done before with, you know, all the instruments you have, not when it's emergency already. So you just need, you know, something. It can be a wooden stick, you know, whatever, something that, you know, can act as a measurement. And then, see, you would just align the Polaris. So let's say, let's figure out the height of this cloud. So I would put this edge to the cloud. Then I would extend my arm sideways or whatever method you're using, as long as each time you do the same. And then I measure, I put the finger where the horizon is, and the top of this box is where the cloud is, okay? So I would measure this distance, which is here around, let's say, 10 centimeters. So now let's assume that the height of the object is, using the sextant, would be, you know, 20 degrees. And that equals to 10 centimeters on my, you know, whatever device I'm using. Which means that the 5 centimeters would give me 10 degrees, right? And if I had 20 centimeters on my device, that would mean 40 degrees, okay? So once you measure this and you calibrate, you can say that many centimeters is that many degrees of the height. So at night, you can just find the Polaris, you know, measure then, you know, this distance, and that's it. And then, because the Polaris is more or less declination of 90 degrees, actually 89.2 or something, even without any corrections, you're gonna have a pretty like accurate reading of your latitude. But then if you wanna go, so in the worst case, you're gonna be wrong not more than 42 minutes, you know, of the latitude. But then you can go for the correction, and it's very easy. So let's say that the Cassiopeia, you know, star, everybody knows, and the Big Dipper are horizontal. Then there is 0 arrow. So whatever angle you read, you just go directly. Now, if a Big Dipper is up and the Cassiopeia is down, that means that you have to add 42 minutes to whatever you measured. Now, if it's the other way around, you have to deduct. So like go minus 42 minutes. Now, if it's something in between, let's say at 45 degrees, and let's say Cassiopeia is down, Big Dipper is up, then, you know, just interpolate, and you just have to add around 21 minutes. So it is super easy to figure out your latitude just using these tools. Make sure at home you practice a little bit, calibrate, and then once your hand is calibrated, it's calibrated forever. Very easy to figure out the error, and then the more accurate you are, take your time, the more smooth the sea is, you'll be just fine. But there's one thing, the Polaris, so let's say you are all the way up in Norway, let's say North Cape, 70 degrees north, like all the way up, then it's pretty hard, to measure. Or if you're in the equator, you're probably not gonna see Polaris. So it just works, the best probably if you are like we are now, and then to the, I don't know, the height of Europe. That's where it's just easiest to measure it. But whenever you see it, you can actually measure it, and it's gonna give you a pretty accurate latitude. Checking the fruit every morning. You just have, to go turn around a little bit, shake it. Check the lemons, and the oranges were going bad. Apple's doing really good. The bananas look kind of bad, but actually they're really good inside, and I would prefer to have this one. It's much sweeter than this one, which is not ripe yet. So yeah, no bad fruit today. We are putting on a water maker because we have used most of the water. And then I guess you're wondering how much water do we use? So this boat has 600 liters of water, in the tanks. And we have just almost used it all in 5 days. So which means we've been using 100 liters per day. And it's 3 persons on board. And we were having showers like almost every day, have a shower. And we didn't really spare, we didn't waste it. And the toilets are also fresh water flush. So we're actually using the fresh water from our tanks to flush toilets. Well, that's how they do these boats these days. Not all of them, but many do, because apparently it stinks less. So I don't know. So we are using 100 liters per day. If you go per person, that would be, let's say, 33 liters per person per day. And that's with showers and not really, sparing it too much. Luckily, we have a water maker, as long as the water maker is working. And this water maker can produce 108 liters per hour. So now we're gonna run it for around 3 hours, and we're gonna be full with our tanks. Since now we've been drinking the water from the tanks, which I've said, it's not usually a practice, but this boat has carbon filter. So whatever you drink from the pipe in the kitchen goes through the, carbon filter, which should be, safe enough. And then again, in case everything breaks or we lose all the water from the tanks or whatever, we still have enough drinking water in canisters and bottles to, come across an ocean. Another problem with the water which is produced by the water maker is that it's pure H2O. There's no, whatever you have to get in water, so the body needs. So if you would be drinking all the time the water which is from the water maker, I guess you would eventually wouldn't be healthy anymore, you would die. Because I guess you need to get all the minerals, electrolytes that you can get only from the water. So some people add all these kinds of salts, or what I'm gonna do, I'm just gonna have a mineral water and drink half of that, just to get a liter of whatever, of the good water, and then combine it with the water from the water maker for the rest of the things. So how does water maker work? It's very easy. So it transforms salt water to fresh water. And because the molecules of water is now H2O is actually like the size of like my nail, very small. And the salt would be the size of my fist, and viruses and bacteria and all other stuff inside would be way bigger, like my fist or bigger. So actually H2O is very small. So now let's assume, okay, this is a kind of a fabric. And you know that if you take a hose of the water and just spray, it's gonna bounce, not much is gonna go through. But if you put more pressure, put it close, then some water is gonna go through it. Now, if this fabric is a very fine membrane, very special one, which is so fine and so high-tech that only H2O can go through, and all the salt and viruses are gonna stay on this side. So you need a lot of pressure to do that. So everything that stays on this side, we're just gonna flash back to the sea. Whatever comes out on the other side is actually a pure water, H2O, and we're just gonna collect it in our tanks, and that's it. It's not a rocket science, a little bit of high tech, these membranes, they're sophisticated, but then you just need a lot of pressure, which you gain with electric pumps, and here it is, fresh water. So the salinator itself, I've said, it's very easy, it's nothing special. But membranes are really sophisticated. So these are like instructions how to use it. It's quite a lot because you don't want to mess it up. If you go wrong with the membranes, which are high-tech, you're done. You can buy a new membrane, which is actually the most expensive part of the water maker. It's actually just a membrane and a high-pressure pump. And the high-pressure pump is not so high-tech. And we caught a fish. I mean, we didn't really caught it. It just, jumped up here. This is the flying fish and whatever is left of it. And yeah, this is it, flying fish. You can see it has these wings and then just flies out. See, now let's just give it back to the sea. We have opened the Genoa for now. I mean, there's not much wind, so we have 11 knots of wind, now doing around 3 to 4 knots. And it's just because we don't want to be too fast, we don't want to get there during the night. So we're just gonna go lazy now, and then later maybe put a Gennaker up. But for now, this is just an easy way to go slowly. It sounds kind of funny, crazy, I don't know, like you don't want to get there like as fast as possible. I don't know, you don't want to. Especially, let's say you're sailing in a Pacific and there's lots of, atolls, the entrances are quite narrow. There's a lot of, reefs. You don't want to enter at night. You always wait for the daylight and also the direction of the sun. Because when you're entering and there's a lot of reefs, always you need to have the sun from behind. If you're going towards the sun and there's reef, you're not going to see them. So you really have to plan your arrival time and landing carefully. And many times it's just like, you slow down for the last night. And then, it's much safer this way. And this one goes to the sea also, because we don't want any stinky fish, as I've said. So you can see this is the wings. Bye-bye, fishy. And it seems like this sheet for the Gennaker actually works really well to get a better shape. So we're not using the normal sheet for Genoa, but just instead this. It opens the sail much more, so you get a better downwind shape. And it works pretty well. So it's time for a special sausage sandwich. So we've done sausages, freeze them, and now this is gonna be the best breakfast. So sausages, which are actually really good, I think it's from Canary Islands. Toast, some ketchup, and that's the way how to start the day. And otherwise, these are actually very good sausages, but I would suggest not having bad sausages in the heavy seas, because your stomach is gonna say no, and you're gonna finish laying down here with a bucket between your legs, probably. So we're now officially in tropics, so we are between 23.4 degrees north and 23.4 degrees south. It is kind of winter time, so the sun is actually a little bit south. We're lucky it's not exactly above our heads where it would be in summer. But again, the sun is strong, so you do want to protect yourself with long sleeves, sun cream and all the other stuff. But let's talk about the boat. So as we're not planning to use the mainsail for the rest of the couple days, because definitely not today, and then we're gonna stay a couple days in Cape Verde, you do want to close it, you see? Because the sun eventually will destroy the sail and it's probably just gonna pop out at the moment you don't really want to do it. Now with the Genoa, so of course when the sail is open it's exposed to UV, and that's how it is. So the more you sail, the sooner the sail is going to need a replacement. But you can see this part, you see on the edge, it's a little bit different color because this is the UV protection. It goes also here. So once you furl the sail, like we can see here on the Jeep, only the UV protection is exposed. So actually when the sail is furled like this, it is protected from the UV. Like on the mainsail, you do have to close we call it lazy back to protect it from the sun. And where does the expression lazy back, so this is the lazy back, come from? So let's say in the old days, or I don't know, you wouldn't have this back. So the sail itself, when you would be lowering it, would just fall on the deck, and then you would fold it on the boom and use some ropes, you know, to fix it on the boom. And then when you would be rising, you would undo these ropes, everything would fall on the deck, and then you would rise it. Now, using this, everything is simplified. So because of these ropes, the sail just, you know, pops up, falls down in the back. So that's why it's a lazy back, because it's easy. And there's this thing with these furlers for the sail. So this is a Genova, and then this rope, which is in this drum. So when I pull it here, which actually goes all the way down to the helm of the cockpit, then you just, you know, furl the sail. Now, if you keep this loose, you see what happens is, this rope really tends to go in between, falls down, you don't see it, you want to furl, and then the rope gets like damaged in here, gets stuck. So the design of these furlers, and this is nothing to do with this catamaran, with the Neel, this is to do with the rig, right? This should be designed much better. It happens to me, you know, a couple of times per season, then I, for some reason, forget, and I damage the rope or just, you know, get stuck. So this needs a better solution. And then I open the windows, so you can see this sheet, you see, going up and down. So it's kind of, you know, either like make it tight up there on the helm, or, you know, whatever, just make sure it doesn't go under the window and pops it up. Always this window, and also the windows on the floor, like all of the stuff, you know, that's sticking out. These ropes tend to get hooked, just as this rail that we had to fix. So, yeah, I'm just gonna close it a little bit. This is another example of UV protection. So the dinghies, they get damaged a lot on the UV. So that's why they use this cover, which is actually attached all the time. This is UV protection. So having this, you can still, you know, use all the things of the dinghy. So it has to be built precisely for the model. And this is, you know, gonna make this dinghy live much, much, much longer. We have some more safety equipment here, which is mostly used if somebody falls in the water, so man overboard. So this one here is just a rope, so you just take it out and you can pass it to the person in the water, or, you know, make a loop around the person so he can grab it. And then this one is a little bit more sophisticated. It actually has this kind of belt that the person can put around and then be pulled out using a halyard. So this one, you can see, you drop it in the water. This is this belt that person, you know, would put around the waist, or just use a halyard, and you can, you know, hard to see, you know, pull somebody all the way out of the water, which is pretty cool. You can just use a halyard, or this boat is really cool. Well, theoretically, we could also use this, which is for lifting a dinghy out of the water. But this boat has something more. So you can see here at the end of the boom, there's actually a shackle, and that's actually, you can use this as a, you know, lifting device for the dinghy also. So we could just use this, which most of the boats usually don't have. So we could use this to hoist the person off of the water. Very useful. And then here, this is just the buoy. So if somebody falls in the water and you want to mark the position, you would just throw it in the water, it would inflate. So even if there's very big waves, you know, you're still going to mark the position and see very well where that person fell in the water. And of course, this is a life raft. So the life raft is actually attached with the rope to the boat, and that would, you know, inflate it and also keep it attached to the boat so it doesn't go away. So here, all you have to do is, you know, cut this thing. So it opens, throw it in the water. It should self-inflate. And then I have already talked about this whistle, which is, you know, high visibility, super loud thing. You just whistle so everybody wakes up, comes to the deck. And then we have another one here. at the helm, so whoever is on the watch doesn't need to leave the helm station, so he can be here, steer, fight with the winds, and then just use this whistle, which is, you know, nice bright color whistle, so everybody knows it's time to wake up and be on the deck very quickly. Now it's time to make emergency compass. I'm sure you've seen this around. So what you need is, well, we're gonna use this compass just to confirm the accuracy. And before I start, I want to check for deviation. I don't want to have any, you know, wires or metal underneath because it would ruin everything. So I can do this like this. So I'm measuring now 150. And if I go low, I can see if there's any metals around, you know, so it would just cause a deviation. So yeah, there's a little bit, but it's, you know, maybe a couple degrees, 5 degrees, which is neglectable. So what you need is, like you always have needles when you're sailing, you have these needles for repairing the sail. And then you do need something to float your needle, so I'm gonna use this. You need water, of course. And you want to keep it low so it's not bouncing too much. So the lower you go, just find a place in the boat which is not bouncing so much. Now you want to magnetize this, and the easiest way is if you use just a normal magnet. This is from, you know, using in house on the refrigerator. Now the key is how you do it. You only want to magnetize one part of the needle. You know, if you magnetize it all, you know, it's obviously not going to work because you want one part, you know, to go towards north, but the other one not. Okay. And you have to go one way because of physics, whatever you learn in school. So I'm just gonna use, you see, half of it and just to rub the magnet towards. Usually you have to do something like, I don't know, 20 times. I mean, the more you do, the better, right? So I don't know, that's like 10, 11. I'll just do more. So the experiment hopefully works. And then you can always check if the needle is magnetized by, you know, putting it next to very small light metal things, you know, to attract them, like those, you know, paper, how's it called, clips. Okay, so that was like quite many times I've done this. So it should be magnetized. I'm not sure, but theoretically should be. So I'm gonna place it now into the water. So now I'm having a little trouble because, so this is a very small like box, right? So the needle was also crashing into the sides, but okay, let's check it now. So let's see with my compass. So it's actually vice versa, right? So the compass is pointing south in that direction, which means north is exactly where the needle is actually pointing. You see, so the needle is pointing north, but my compass is pointing south, so it's, you know, the same. The only problem is when it hits the walls. So you see, I can turn it around, and eventually, you see, it comes back very quickly. See, it does work. I would need a bigger container, but you can obviously see that it's magnetized, so when I see you release it, it tends to turn towards north. Well, the bigger container is definitely needed. And yeah, I can confirm now with my compass that this is pretty accurate. I would say, like, this is super accurate. Good stuff. So I'm not a coffee drinker, but this is an interesting way of making a coffee. Oh, so the coffee is happening, yeah. So why is it lifted? It's lifted just because these burners are really strong and you don't want to burn all the coffee. So if you're more like high-tech in a coffee, which I'm not, I don't drink coffee at all, but it's a very interesting way. I mean, I would say it's too high, but actually it works. It's really good. Yeah, go on, don't burn it. Oh, so this is called Italian coffee, right? Italian mug, or?
It's a mocha pot.
Mocha pot, yeah. And then you want to cool it down very quickly, so
so it stops
from cooking.
Stops cooking.
Otherwise, it could be overcooked, right?
Yeah, if it's over extracted, it pulls out more now of the bitter flavors. Now the second boat popped up on ice.
So this is Bilowini. It's also a part of the ARC. So it's 11 miles away, and then this one, Nanook, which is also 12 miles away. So they're very close, going to the Cape Verde and then crossing to Caribbean. My needle compass showed out to be like very accurate, and why wouldn't be? You know, it's magnetism. If you magnetize a needle, well, of course it's going to point north. It's just the same as this. I mean, there is not much difference. And then you wonder, like, what about the compasses we have on board? So every boat always has a compass, right? And when everything breaks, yeah, I'm just going to use this one. I'm going to find my way to safe haven. Well, not exactly. So why are all the compasses covered? They also always have a cover. And there's a really good reason. It's not just, you know, like fancy stuff. The thing is, if you keep it in the sun, it would heat up, cool down, heat up, cool down. Eventually, the liquid inside is just gonna, you know, like drain out. So this is the way how to protect your compass for many years. Now, is this compass accurate? Well, let's see. My handheld definitely is. So this one is saying now around 230, and this one is looking around 240. So roughly we have a 10-degree difference. And you know, you might say this one is wrong. Well, we can confirm it here because we have a magnetic heading here, which also says around 240, while this one is around 230. So we can confirm that this compass is 10 degrees off. So why is it like that? It's because you cannot say variation is the problem, because the variation affects this one and this one just the same, but it's about the deviation. So this position of compass here, you see there's a lot of metal around and there's some wires inside, electricity, which just messes up the compass. And that's with all the boats. Actually, this boat is pretty good because most of the boats have much bigger deviation error. So it's a very bad position, because when everything goes off, you trust this guy, but he's not accurate. So you should always test your compass to make sure how deviation is affecting him. And now you're thinking like that, yeah, Igor has to be wrong. Like, what does he know, you know? Like, the guys who are building this boat and putting this compass, they gotta know better. Well, it's, well, they do, and they know this deviation. So when they're using a boat, they know. And every seaman knows that compasses which are now integrated in the boat are affected by deviation. So that's why I always carry this one, because I can put it away from many, you know, metal parts, and it's not going to be affected by deviation, only variation, and, you know, I'm on the safe side. So always carry this one, and I can check the main compass of the boat with this one. And then just, you know, the error is 10 degrees, and I just count it in. And then you would think like, why don't the designers of the boat or builders just put that compass somewhere where it would be the most accurate? You can get it? I don't know. That's what I'm asking myself. And actually, that's what I'm asking now all the designers is, just please put these compasses the way that they're not going to be affected by, you know, metal parts and electricity of the boat, because there's people who don't really know this and they might get in trouble. They're going to open the compass, follow east to get to the Caribbean, but instead they're going to get to South America. Well, let's talking about water maker. Let's take a look how it is, how it works, how it looks. Turn on the lights. It's very loud and it's very hot in here. Okay, so I'll show you how it works. So this is a generator, and we need this because we need a lot of electricity to run the water maker. And this is telling you the pressure on the membrane. This tells you how much fresh water per hour we're producing. And this is the pressure of a feed pump. So this is the pump that's actually, you know, producing the high pressure to go through the membrane. These are the filters. So when the salt water goes inside, it's already filtered so that we don't damage the main membrane. So the pressurized water goes through the black hoses, and it goes in here. So these are two very long tubes, you can see here, and these are the membranes. This is where, you know, the salt is separated from the fresh water. These are the long membrane. This is the expensive part. So this is just the commands. This is the high high pressure, putting the water in here, like very high pressure, and then just squeezing H2O through the membrane and letting the salt, virus, bacteria go back to the water, seawater. So it looks complicated, but actually like pretty easy to understand how it works. Is that we have set a waypoint to where we're going in Mandela, and then we're using so navigation here. So we have this waypoint, and it tells us when we arrive there and what's the distance. So by controlling the speed, it's very easy to figure out what is our arrival, and you don't have to calculate it each time, you know, like how much more, what's the distance. So it's pretty cool to know that. And then another thing is I've set here a special screen just for myself. So I have a magnetic variation. I was talking a lot about, you know, compasses, variation. So magnetic variation, this is the data you want to know. So the compass is off by 8.5 degrees at this where we are right now. It's going to keep changing. And then very interesting data is VMG, which is called velocity made good. It's actually the speed of approaching, your speed going directly to the wind. If it's minus, it's your speed going, you know, 180 from the wind. It's basically telling you how efficiently you're sailing upwind or how efficiently you're sailing offwind. And then of course the sea temperature, 26 degrees. Looking forward to jump in the water as soon as we get to Cape Verde. I hope there's no sharks and anything in the water, but I believe not, and really looking forward for the swim.